Hi, my name is Nikos Tsikoudis, and today I will talk about the duplicating snapshot computations. I'm currently with datometry, but this work was conducted while I was a student at Brandeis University with my advisor Liuba. Nowadays, retrospective computations on historical data are essential for tasks that involve audits, forensics, or predictions. In a typical example, a factory where employees have certain skills maintains some important safety policy. After some accidents, investigators want to check when was the policy first violated or how many times it has happened. A computation answering such questions can be inefficient, especially for very long histories. So this work focuses on how to make them more efficient. First, let's see how retrospective computations can be implemented for everyday SQL applications. We assume a snapshot system integrated with a data store. It allows to create page granularity snapshots using an efficient copy on write technique and store the snapshot persistently. So applications using the snapshot system can take snapshots of their state. In the factory example I mentioned earlier, we assume this shift assignment table that stores employees and their skills. We have created 4 snapshots showing the employees on shift when the snapshots were created. Now, consider the factory safety policy where at least one worker with a specialized skill has to be present at all times. And we want to find out the first time the safety policy was violated. To perform this after-the-fact analysis, we need to run SQL queries over multiple snapshots of interest and aggregate on the results of the queries. Now, here is how we can express such a retrospective computations using a language we have developed in an earlier work. The highlighted query in green will run on each snapshot separately, performing an in-snapshot computation, which returns the snapshot ID if the policy was violated. In addition to that, a cross-snapshot computation, the one highlighted in blue, will perform the mean aggregate function on the snapshot timestamps or the IDs in order to calculate the final result, which is the first time the policy was violated. The in-snapshot computations in general can be optimized using SQL optimizers, but currently there are no satisfactory methods for optimizations for computations that compute across multiple snapshots. So our goal is to develop such optimizations. To explain the inefficiencies arising in cross-snapshot computations, I will have to explain what happens under covers when we create snapshots. We use a system called Retro, which introduces a snapshot system in Berkeley DB. A snapshot is a consistent, persistent set of immutable pages of the disk, reflecting the state of the database at declaration point. The snapshot pages are stored in a separate disk, so the database is not affected by the snapshots. And to the programmer, the snapshot looks exactly like the database. So any query that can run in the database, it can also run on any declared snapshot. The snapshots are created using a page-level copy-on-write technique. On this transaction timeline, let's consider the declaration of snapshot SI, followed by transactions that modify pages P and Q, followed by the declaration of the next snapshot SI plus 1. When the transaction commits the updates to pages P and Q, Retro copies the pages before the modification into the snapshot disk, since these pages reflect the snapshot SI. In addition to that, the Retro indexes the snapshot pages, and the index records show the pages that have been modified between the declaration of the two snapshots. In this case, we show the diff between SI and SI plus 1. Note, in this example, snapshot SI and SI plus 1 share all the pages except P and Q. So if a query does not access records on pages P and Q, the results of the query as of SI and as of SI plus 1 will be identical. Clearly, computing the same query twice will be wasteful. Instead, we can simply reuse results. The optimizer I will describe next exploits the diffs in the index to detect and eliminate such redundancies. We designed and implemented READ, an optimization framework for retrospective computations that use retro to run queries iterating over multiple snapshots. There are two types of redundancies we consider. Redundant in-snapshot computations when query returns identical results for multiple snapshots, and redundant cross-snapshot computations when we compute aggregations like min or max over query results. If the query results do not change, then min or max values will not change either. So we can avoid the aggregations on the identical results. Also, it's important to note here that redundancies are common when snapshots compute snapshot computations access cold data. And in many common workloads, the majority of the data is cold. Our approach to identify redundancies is to exploit the retro snapshot index that keeps track of the modified pages between snapshots. When a query queue runs on the first snapshot, we track a set of accessed pages, we call it PAS. And before the query runs on the next snapshot, we check if any of the accessed pages have been if any of the accessed pages are changed between the two snapshots. And we do that by checking the PAS and if intersection. If the intersection is empty, we can safely reuse results. These low-level index-based checks are efficient and fast. They are independent of how many snapshots we have created or how many snapshots we are interested in analyzing. They are also language independent. Once implemented in the snapshot system, they work for any language or application. To the best of our knowledge, this is the first language-independent optimization approach. Prior redundancy elimination technique we have studied work at language level, so they are language dependent. Now, without read, cross-snapshot computation executes like this. There is a loop that iterates snapshots, executes a query on each snapshot, collects the results, and performs the cross-snapshot computations. With read, the execution runs as follows. At step 1, we track the current snapshot, in this case SI. Let's ignore step 2 for a second. At step 3, we execute the query queue on snapshot SI. We track the accessed pages, and we cache the results of queue. At step 4, when the query completes, read will calculate the next divergent snapshot SJ, for which the accessed pages have been modified. At step 5, we perform the cross-snapshot computations. Now, in the next iteration, at step 2, we check if the current snapshot is created earlier than the divergent snapshot SJ. If yes, we can safely skip the query evaluation, go to step 5, and reuse the previously cached results. This gives a flavor of our optimization approach to cross-snapshot computations, and more details can be found in our paper. To evaluate read, we want to check how effective it is at eliminating duplicates. There are several factors we are considering here, and one is how cold or cold the data is. Duplicates are common when retrospective computations access infrequently modified data, and in many common workloads, only a small portion of the data is hot and the majority is cold. Another factor is the size of the footprint of the query. Read is especially beneficial with small footprints and especially for point queries. Another important point here is read duplicate detection checks the diffs at the page level. These checks are fast, but they can also be coarse because and we can have false negatives. We get a false negative when we cannot detect a duplicate, when the query, when the records accessed by the query do not change, but other records in the same page have been updated. We have developed an analytical performance model to measure the impact of the false negatives. We validated it using both synthetic and real-life datasets. And it shows that READ provides high performance benefits when we analyze cold data despite the coarse detection. On the real-life dataset, it gave us up to 88% improvements. We also evaluated the overhead that READ introduces, and it was negligible in our experiments. To conclude, READ is the first language-independent optimization framework for retrospective computations. It combines benefits of standard SQL optimizations for in-snapshot computations with efficient low-level cross-snapshot optimizations. In the paper, you can also find a correctness theorem for our detection approach and the proof. The analytical performance model that measures the impact of the false negatives, and a component that an optimization component that exploits the semantics of aggregation operations. And with that, I would like to thank you for watching this video, and feel free to contact me if you are interested in learning more about READ.